Hello, welcome back to part 2 of point estimate and confidence interval. I am Hemakumar Kasala and we start back from where we left in part 1 and proceed to learn on how to apply the general expression for confidence interval to sample proportion distributions, how to apply the general expression for confidence interval to sample mean distributions, what is the bound on error and how to arrive at sample size based on bound on error, what is t-distribution and when to apply the same, and finally, summarizing the key points to remember in handling the confidence intervals. This is where we left in part 1. The value of sigma x bar depends on the kind of the sample statistic. We discussed two kinds of sample statistic distributions, namely sampling distribution of sample proportion and sample mean distribution. We will understand how to arrive at the value for sigma x bar for each of the two distributions in this lecture. And we start with sampling distribution for sample proportion first. In case of sampling distribution of sample proportion, the long run mean value for sample proportion of success p, that is mu p, equals population proportion of success pi. Mu p equals pi. The standard deviation of the probability distribution for p, sigma p, equals square root of pi multiplied by 1 minus pi divided by n. Since the population proportion pi is not known in most of the cases, it has to be estimated using the known sample proportion p. Especially in a large sample case, we can replace pi with p in the formula for sigma p and arrive at sigma p as square root of p multiplied by 1 minus p divided by n. Therefore, the 95% confidence interval with an estimated sample statistic, that is sample proportion p, is p plus or minus 1.96 times square root of p multiplied by 1 minus p divided by n. P plus 1.96 multiplied by square root of p multiplied by 1 minus p divided by n is the upper end of the confidence interval, and p minus 1.96 times square root of p multiplied by 1 minus p divided by n is the lower end of the confidence interval. This confidence interval p plus or minus 1.96 times square root of p multiplied by 1 minus p divided by n can be used as long as the following requirements are met. 1. Sample is a large sample, that is, n pi is greater than or equal to 10 and n multiplied by 1 minus pi is greater than or equal to 10, where n is the sample size and pi is the population proportion. 2. Sample size n does not exceed 10% of the population size if sampling is done without replacement. And 3. Sample is a random sample. The general expression for large sample confidence interval for a population proportion pi is p plus or minus z star times square root of p multiplied by 1 minus p divided by n, where z star is the z critical value for the chosen confidence level. For 90% confidence level, z star equals 1.645. For 95% confidence interval, z star equals 1.96. And for 99% confidence interval, z star equals 2.58. Higher the confidence level, higher is the reliability. Misses the population characteristic only a fewer times, but lower is the precision, since interval is wider. Lower the confidence level, lower is the reliability. Misses the population characteristic a little more often, but higher is the precision. That is, the interval is narrower. And hence, the mid-value 95% is more often used to balance between the reliability and precision. The confidence interval p plus or minus z star times square root of pi multiplied by 1 minus pi divided by n captures the population characteristics x% of the times, implies the sample statistic falls within the interval pi plus or minus z star times square root of pi multiplied by 1 minus pi divided by n x% of the times. Extent of this interval on each side of pi, that is z star times square root of pi multiplied by 1 minus pi divided by n, is called as the bound on the error of estimation, represented by B. Since the sample statistic P lies somewhere within this interval for X% of the samples drawn, the error in estimating pi is bound by this interval. Bound on the error estimation B can be used to choose the sample size n required to estimate pi. Since B equals z star times square root of pi multiplied by 1 minus pi divided by n, choosing an acceptable value for B, we can calculate the required sample size n for a chosen confidence interval and thus z star and a population proportion pi. We can choose a value of say 0.05 for B, meaning we aim to estimate pi within the bounds pi minus 0.05 and pi plus 0.05, and choose 95% confidence interval, that is z star equals 1.96. Then from B equals z star times square root of pi multiplied by 1 minus pi divided by n, we can derive the required sample size n as n equals pi multiplied by 1 minus pi multiplied by 1.96 divided by B the whole square. When pi is not known and cannot be estimated with reasonable accuracy by other means, we could choose the maximum value for pi multiplied by 1 minus pi in the expression for n. The maximum value for pi multiplied by 1 minus pi results in a maximum value for n, and that can be considered as a compromise given pi is unknown. The maximum value for pi multiplied by 1 minus pi is arrived by choosing value pi as 0.5, and thus pi multiplied by 1 minus pi equals 0.5 multiplied by 1 minus 0.5, that equals 0.25. Substituting 0.25 for pi multiplied by 1 minus pi in the expression for n, we get n equals 0.25 multiplied by 1.96 divided by 0.05 the whole square, and that approximates to 385. Therefore, we can state with 95% confidence, choosing a sample size n as 385, we can achieve P, the estimate for pi, within pi minus B and pi plus B, where the bound on the error estimation B equals 0.05 for all values of pi that satisfy the large sample requirement, wherein n pi is greater than or equal to 10 and n multiplied by 1 minus pi is greater than or equal to 10. Note, the above requirement is important because the confidence intervals arrived based on the assumption that the sample statistic distribution is normal. That summarizes the part on estimating the confidence interval for the population proportion pi using the estimated standard deviation, standard error, bound on error estimation, and choosing the sample size. Let's turn our focus on estimating sigma x bar and subsequently the confidence interval in case of sample mean distribution. In case of the large sample, the sample mean distribution is close to a normal distribution as per the central limiting theorem, with the mean of the sampling mean distribution mu of x bar equals mu, that is the population mean, and standard deviation of the sampling mean distribution sigma x bar equals sigma divided by square root of n, where sigma is the population standard deviation and n is the sample size. A large sample for a sample mean distribution implies the sample size n is greater than or equal to 30. Therefore, for example, a 95% confidence interval in case of sample mean distribution equals x bar plus or minus 1.96 times sigma x bar, where x bar is the sample mean statistic and sigma x bar equals sigma divided by square root of n, where sigma is the population standard deviation. The assumption here is that the population standard deviation sigma is known, which is not often the case. We'll address the unknown sigma case soon. The general expression for confidence interval for a sample mean distribution equals x bar plus or minus z star times sigma x bar, where z star is the critical value corresponding to the chosen confidence level. The above general expression for confidence interval for a population mean applies when the sample size is large, that is, n is greater than or equal to 30. When the sample size n is less than 30, the sample mean distribution does not remain normal in all cases, and hence the validity of applying the above general expression fails in such cases. However, where the population distribution itself is normal, even a sample size n less than 30 results in a sample mean distribution that is normal. Therefore, the above general expression for confidence interval for a population mean applies when the sample size is large, that is n is greater than or equal to 30, or the population distribution itself is normal. Normality in the population data can be verified using, as discussed in our earlier lectures, either the normal probability plot or the box plot. Ensuring the sample mean distribution is normal, let's look into the most common case where the population standard deviation sigma is unknown. In reality, unknown standard deviation sigma is a much more common scenario than cases with known sigma. Does the general expression for confidence interval for population mean apply in such cases? The answer is no. Let's understand why and find the way forward. Sigma x bar equals sigma divided by square root of n, where the population standard deviation sigma is known and fixed. In the absence of the knowledge on sigma, one can estimate the sample mean standard deviation sigma x bar using the sample standard deviation s in place of sigma, as in sigma x bar equals s divided by square root of n. Unfortunately, s is not a constant. It varies with every sample, unlike sigma. Therefore, sigma x bar is small when s is small and sigma x bar is large when s is large. This introduces the larger variance in sigma x bar. And in addition, the variability associated with x bar between samples introduces double variance in the confidence intervals. Therefore, the general expression x bar plus or minus z star times sigma x bar needs some correction. The correction is brought in by using a t-statistic from t-distribution instead of z-statistic from standard normal distribution in the above expression, as in the general expression for confidence interval equals x bar plus or minus t times s divided by square root of n. The t-distribution is a distribution for the t-statistic, and unlike the z-distribution, t-distribution is not a single distribution but a set of distributions, each distinguished from one another via the degree of freedom df. Degree of freedom df equals sample size minus 1, which equals n minus 1. Figure shows t distributions for 4 different values of df. Smaller the df, shorter and wider is the t distribution. Larger the df, taller and narrower is the t distribution. Finally, when df exceeds 30, then it tends closer towards the normal distribution. Coming back to the general expression for confidence intervals when sigma is not known, x bar plus or minus t times s divided by square root of n. The critical value t for a chosen confidence interval is picked from the t-statistic table instead of z-table. The way to read and pick the t values from the table is as follows. Calculate df. df equals sample size minus 1, which equals n minus 1. Example, for n equals 21, df equals 20. Select the row corresponding to 20 in the first column. Let's choose the confidence level as 95%. Select the column corresponding to the chosen confidence level. Pick the t value from the table at the selected row and the column, which equals 2.09 in this case. Therefore, the 95% confidence interval for the population mean when the population standard deviation is unknown equals x bar plus or minus 2.09 times s divided by square root of n, where x is the sample mean and s is the sample standard deviation and n is the sample size. Notice that for 95% confidence interval, z critical value equals 1.96, whereas t critical value equals 2.09. wider. T critical value increases as df reduces, and T value reduces and approaches Z value as df increases. The reduction in the spread or variability within the T distribution as df increases is due to the possible reduction in the variability within the sample statistic distribution. With large sample sizes, that is larger values of df, the variability within S reduces significantly, that the T distribution coincides with the Z distribution eventually. Note, confidence intervals using the T distribution x bar plus or minus T times S divided by square root of n is used when sigma is not known, and importantly, either the sample size n is large, that is n is greater than or equal to 30, or population distribution is close to normal. These two conditions ensure that the sample statistic distribution is normal. Let's take an example. A cardiac care center in a particular city collects data regarding the time taken between the consultation date where a surgery is suggested to a patient and the actual day the surgery is carried out. Data is collected for two kinds of surgical procedures, bypass and angiography. Sample data is collected from 539 and 847 patients respectively. Mean wait time and standard deviation for each of the samples are calculated. Let's estimate the confidence intervals for the true mean wait times for each of the two surgical procedures. Let's consider the bypass case to begin with. Sample size of 539 is much higher than 30, and hence the requirement that n greater than or equal to 30 is sufficiently met. And the sample mean wait time can safely be assumed to be part of a normal sample mean distribution. Sample standard deviation is 10 and the population standard deviation is not known. Therefore, we estimate the 95% confidence interval using the T statistic as in 19 plus or minus T critical value multiplied by 10 divided by square root of 539. Since df equals 539 minus 1, which equals 538, and 538 is much above the maximum value 120 that's available in the T critical value table, we pick the T critical value from the Z critical value row for 95% confidence interval, and thus the T critical value equals 1.96. Therefore, the 95% confidence interval is 19 plus or minus 1.96 times 10 divided by square root of 539, which equals 19 plus or minus 0.844, which in turn is an interval between 18.156 and 19.844 days. Based on the sample, we are 95% confident that the true mean wait time for bypass surgery is between 18.156 and 19.844 days. The interval is fairly narrow, suggesting that the estimated confidence interval is relatively precise. Similarly, 95% confidence interval for true mean wait time for angiography can be estimated as between 17.394 and 18.606 days. The 95% confidence interval for true mean wait time for angiography is narrower than that for bypass surgery. The reason being, the sample standard deviation S for angiography is smaller than that for bypass, and the sample size N for angiography is larger than that for bypass surgery. Since the sample sizes are much higher than 30, it is safe to assume that the respective sample mean distributions are near normal, and no need to verify if the populations are normally distributed. But for the sake of understanding, box plots for both the samples are presented. The distribution looks close to normal, but for the outliers in both cases. Since the sampling sizes are large, we could still go ahead with the T confidence intervals. Note, normal probability plots can also be drawn to verify the normality. Going back to the general expression for confidence interval for a population mean, x bar plus or minus z critical value times sigma divided by square root of n when the population standard deviation sigma is known and the sample size is large, that is n is greater than or equal to 30, or the population distribution itself is normal, we can identify the bound on error estimation b for a population mean from the above expression as b equals z critical value times sigma divided by square root of n, where the z critical value depends on the confidence level. It is always preferred that the bound on error estimation b remains relatively small so that the population mean mu is estimated within a small b. The confidence interval remains small and Ci is more precise in estimating the population mean. In order to achieve a b value that is relatively small, the sample size n should be carefully chosen. Higher the sample size n, lower is b for given values of sigma and confidence level, that is the z critical value. The sample size n to achieve a desired bound on error estimation b is given by n equals z critical value multiplied by sigma divided by b the whole square. Larger the population standard deviation sigma, larger will be the sample size n required. Smaller the required b, larger will be the sample size n required. The sample size formula n equals z critical value multiplied by sigma divided by b the whole square requires a known population standard deviation sigma. But sigma is not known in most cases, hence needs to be estimated in one or other ways. One of the possible ways is to carry out a preliminary study and arrive at a sample standard deviation s that can be used in the place of sigma. Another possible way, when the population is not too skewed, is to calculate the range in the population, that is, largest value minus the smallest value, and divide it by 4 to fairly roughly estimate sigma. Let's take an example. Let's consider a study aimed at estimating the mean cost of textbooks in a given quarter in an university. Let's say the aim is to estimate the true mean cost of the textbooks within $20, that is b equals 20. What is the sample size of books n required to achieve a bound on error estimation b equals 20 using a 95% confidence interval? To calculate n equals z critical value multiplied by sigma divided by b the whole square, we need to know the population standard deviation sigma. If we know that most of the books cost between $50 and $450, we can estimate sigma using sigma equals range divided by 4, which equals 450 minus 50 divided by 4, that equals 100. The sample size n equals 1.96 multiplied by 100 divided by 20 the whole square, which equals 96.04, and it is rounded up to 97. Therefore, the sample size required to estimate true mean textbook value within $20 using a confidence interval of 95% equals 97 or more. Points to remember while dealing with point estimate and confidence intervals. A point estimate doesn't provide any information on its accuracy while estimating the true mean. The point estimate can be anywhere within the spread of the sample statistic distribution. Hence, it is always good to accompany the point estimate with a confidence interval. The confidence interval defines the bound on error estimation b that provides some information on accuracy. With a certain confidence level, states how far maximum the true mean could be away from the point estimate. The 95% confidence interval does not mean 95% of the population data is contained within this interval, or 95% of the times the sample mean x bar arrived out of samples of same size each time lies within this interval. High confidence level, though desirable, can lead to wider interval and thus lower precision. Best strategy to reduce the width of the interval is to increase the sample size. Important to decide on the sample size during the early stages of data collection based on the desired precision, that is, low bound on error estimation. Assumptions play an important role in the correctness in the estimation of the confidence interval, correctness of interval width, and success rate for the chosen confidence level. The assumptions in reality are never perfectly met. For example, normal distribution for the population characteristic. Therefore, it is only practical to look for plausibility in the assumption. That is, assumptions are approximately met. That should do. The assumptions that should be plausibly met are: 1. Samples are drawn using random sampling. Process of drawing the samples should ensure the above assumption is met. Number 2. Sample size n is large enough that sampling distribution of the statistic, either p or x bar, is normal. In case of sample proportion p, it is np greater than or equal to 10 and n multiplied by 1 minus p greater than or equal to 10. And in case of sample mean, it is n greater than or equal to 30, or the population itself is approximately normally distributed. And 3, and the final one, is the sample size is not larger than 10% of the population size when the sampling is done without replacement. This is also ensured through the process of drawing the samples. That brings us to the end of the lecture on point estimate and confidence interval. Please leave your questions and comments if any, and I'll revert back as soon as possible. See you again with the next topic soon. Bye.